Our paper presents a new algorithm for pruning neural networks that is computationally efficient and comes with mathematical performance guarantees. Here is a diagram of a network with multiple layers. Each layer consists of a linear mapping followed by the pointwise application of a nonlinearity. The cost of the linear layers is determined by the number of non-zero entries in this matrix W, so the number of connections between the input nodes and the output nodes. So it is natural to ask if we can accomplish the same tasks with a network which looks something like this here on the right in place of something looking like this here in the middle. Our pruning technique, net trim, accomplishes this reduction and in turn leads to computational savings in the operation of the network. And perhaps surprisingly, this model reduction incurs no penalty in the accuracy of the network. So unique features of our framework include that it is post-training. It starts with a pre-trained network already in place, and it uses convex programming, along with allowing very scalable algorithms, allows us to derive mathematical guarantees about its performance. So here's how it works. So we're giving a trained neural network with ReLU activations. So along with the inputs and outputs of this network, the training gives us these responses Y at all the interior layers of the network. So with these responses in hand, we work layer by layer, and so we fix the inputs and the outputs to a given layer, and then we ask if there is a sparse set of weights that preserves this input-output relationship. So we do this by setting up an optimization program. We use the L1 norm as a convex proxy for the sparsity of the connections, and then we define a convex feasibility set that ensures the response does not change too much. So in our particular case, this set penalizes deviations only on the active outputs. Here are our mathematical results. So after retraining each layer by solving our convex programming, we can bound the total discrepancy in the network. So this means that the new set of sparse weights responds to the training data in almost exactly the same way as the original dense network. We also have a sampling result, which provides a lower bound on the number of training examples we need to discover a sparse network. So here's a simple stylized numerical result where we can see that we get almost exactly the same classification rule while using only 7% of the weight. So this is a graphical depiction of the entries of the matrix W, both before sparsification and after sparsification. As a final comment, we have released a scalable implementation of NetTrim implemented using the alternating direction method of multipliers, and the Python code is available at this link.